Welcome to our discussion on Chapter 3, Quantitative Demand Analysis. In Chapter 2, we discuss the things that impact the direction of changes to supply and demand, qualitative sorts of things. Now we're going to talk about quantitative measures of demand, those that are shifting or those that cause a move along the demand curve. It's really important for businesses to think about these kinds of things. They want to not only know that something is going to change, they want to be able to estimate approximately how much something will change. So, for example, how much will supply decrease if a new tax is imposed? How many additional deals can we close if we increase our advertising by 4%? If we're able to close those additional deals, do we have the staffing to support those new contracts? How much revenue will these new deals bring in? These are all questions about the magnitude of the change. Now on to the material in the chapter. We're going to talk about elasticity, actually several measures of elasticity around the demand curve, but also know that we use elasticity to measure lots of other things, not just supply-related things also, but many other things in economics. What is elasticity? So let's start by defining it. Elasticity is a measure of the responsiveness of one variable with respect to a change in another. So for example, at the top here, I put elasticity, we use an E, and when I write it, I often write it with a little curly like that. Elasticity of A with respect to B. So how much does some variable A change in percentage terms when B changes by some percent? And we'll go through a number of examples here so we can make this make more sense. It should be noted that if you get a positive value, that means the two variables move in the same direction. If you get a negative value, that means the two variables move in the opposite direction of each other. Now let's start with the price elasticity of demand, or what this book calls its own price elasticity of demand, really trying to get you to focus on the fact that they're talking about the price of some good X and the impact that that price change has on that particular good's demand. So they're just trying to make you really know we're talking about the price of this good affecting the quantity of this good. That's why they have the word own in there. So we're going to denote this as elasticity of the quantity of X with respect to the price of X, or the change in the quantity demanded of X when there's a change to the price of X. I'm going to write this out a little bit differently for you just so that you can see what this formula would look like. So if we were going to calculate this and we had 2 points along the demand curve, we would do the second point where you end up minus where you start over where you start. That's going to give us the percent change in a proportion, not really a percent. We'd multiply it by 100 if we were talking about percent. And we'll do a couple of examples of this to make sure that you are comfortable with how this works. And then the price where you end up minus the price where you started over the price that you started at. This is really a measure of how responsive quantity demanded is to a change in the price of the good itself. In other words, if the price goes up by 1%, what percent does the quantity demanded go down by? That's what the elasticity is going to be able to give us. So let's look at this on a demand curve. I like to draw in some points and make up numbers associated with this just to kind of make it easier to get a sense of what's going on here. And I'm not going to do all of the math yet. We'll do that in a minute, but I want to be able to get you thinking about this. So let's say, for the sake of argument, that this point here is the price of 20 and this point here is the price of 19. And we're moving from a quantity of 1 to a quantity of 2. If I would just think about this equation, kind of big picture here, the denominator here, that change in price, it's a small change. It's only $1. That change in price is only $1, but it's $1 when we started out at 20. So that's only a 5% decrease in price. Now I say only a 5%, but only a 5% decrease in price when the change that I get when I go from 1 to 2 is 100% increase. So up here at this top part of the demand curve, when I change price a little, the quantity demanded changes a lot, right? So I'm thinking about that equation, and I'm just going to use these numbers here. Our change in quantity demanded was an increase of 100%, right? We went up by a whole 1 or 100%. Our denominator, though, the price went down by only 5%. It's relatively small. This is going to be a big number. Big numbers, far away from 0, are elastic. So if I were to do the math on this, I would have a very big number far away from 0. I'd have minus 20. The elasticity between point A and point B is quite large, minus 20. As I move down the demand curve, the change in price, even if I kept going down by $1, in percentage terms, that change is going to get larger and larger because $1 as a percent of where I started gets bigger. And the quantity change is going to get smaller because each time I change by 1 unit, I'm comparing that to where I started, and 1 unit is nowhere near as much of 2 as it was of 1. So up here, I'm seeing a very elastic response. And this is always how this works. When the elasticity in absolute value is greater than 1, then we would say the item, whatever it is, in this case, the quantity demanded, is elastic. When you hear elastic, just think very responsive. A lot of times I think like rubber band, right? When I pull a rubber band, it's very elasticy. I pull a rubber band back and, I can fling it across the room. It's very responsive. So if the elasticity is greater than 1 in absolute terms, then it's elastic. When we reach the point that happens to be the midpoint on this demand curve, we're going to find that our demand is what's called unit elastic. So when our demand in absolute value is equal to 1, the demand curve is unit elastic. At the point of unit elastic, we actually have the maximum revenue that the firm can be taking in. Or if we're talking about a market demand curve, the total revenue that could be generated in the market is highest at this point where elasticity happens to be 1. This is just a mathematical fact. It's always at the midpoint of the line if the line is touching both endpoints and we have a linear demand curve. If I'm down here at this end, let's kind of work backwards. If I'm down here at this end and I increase price by $1, let's say from $1 to $2, and that causes me to have, instead of 19 units demanded, it causes me to have 18 units demanded. Well, that 1 unit change, that 1 unit decrease in demand is a little bit more than 5%, right? 1 out of 19. That's a little bit more than 5%, but my price has gone up by 100%. So my demand isn't moving a lot compared to how much my price is moving. So let's just put this in here, and let's say that that decrease in demand is about 5.25%. That increase in price is 100%. Our demand here is very small. It is 0.05. When our demand is less than 1, between 0 and 1, we say that demand curve is inelastic. People aren't very responsive to a change in price. So our price went up a lot. Our quantity demanded only went down a little. So in this range, we are inelastic. This total elasticity test is really talking about the impact that elasticity has on revenue. So let me clean this up and we'll talk about that a little bit more. So to talk about the total elasticity test, We're really looking at how elastic is the demand curve at that point of interest and what would happen if we change the price. So we know already that at the unit elastic point, we would have the maximum revenue. Remember, price times quantity is the revenue. So that square I just drew in there, that would be the revenue if we were at the unit elastic point. Now, it isn't the case that firms are trying to maximize revenue, but it's just a point to help us understand what happens when we move price and how does that impact revenue, because revenue minus cost is our profit. Now, if we are above that unit elastic point, we're at a price higher than that. Quantity is very responsive to a change in price. That means if we decrease price a little, we'll increase quantity a lot. That should mean that our revenue goes up. So if I'm in the elastic range, I can decrease price to increase revenue. We know at the unit elastic point, that's the place where revenue is going to be maximized. And if we're in the inelastic range, it's the opposite of what we see in the elastic range. Let's think about that again. If we're in that inelastic range, we can do a large increase in price, right? It's only $1, but it's 100%. And we're going to have a small decrease in quantity demanded. So a small increase in quantity demanded with a big increase in price. If we increase price when we're in that inelastic range, we can increase the revenue to the firm. So we can use this total elasticity test to help us decide at different points as we discuss things, should we try to increase the price at this point or should we try to decrease the price at this point? If the focus is on what will our revenue be. We've got two other graphs I want to look at when we start talking about price elasticity of demand, or really any elasticity. These are for illustration. The demand curve on the left is perfectly horizontal. This we would call perfectly elastic. This would occur when we have an elasticity that's equal to negative infinity. No change in price, right? We're moving along the demand curve. We might consume more or less of the good, and it's completely independent of the price. The graph on the right is perfectly vertical, and we call this perfectly inelastic. This happens when elasticity is 0. The producer can change the price, and we are not responsive at all. So no matter what the price is, we're going to buy the exact same amount of the good. Now, neither of these are perfectly illustrated out in the real world, but this is just to give you an idea of what that would look like. And the way that I remember which one of these is which, the more it looks like an E shape with the axes, it's elastic. And the more it looks like an I shape, it's more inelastic. In the same fashion that we talked about things that cause demand to shift, we also want to talk about the factors that impact the elasticity. So there are 3 key factors I want to talk about today. The first of those factors is the availability of substitutes. If there are lots of substitutes for a good, then that good is more elastic. So an example from the textbook, they note that whole milk has an elasticity of negative 1.1, which is fairly elastic, but milk in general has an elasticity of negative 0.2. Whole milk is a lot more elastic than the more general category of milk. If I want to drink milk and whole milk is relatively expensive, I could get 2%. I could get oat milk. I could get almond milk. There are lots of substitutes for whole milk. So if the price of whole milk goes up, I may shift to 2%, I may shift to skim milk. But milk in general, there are not lots of substitutes for milk in general. Another factor is time. In general, goods and services are more inelastic in the short run than in the long run. If you think about this, in the long run, we can change our consumption much more easily than we can in the short run. For example, my demand for diesel that you would put in like a diesel truck is fairly inelastic in the short run. I own a diesel truck and I've been driving that diesel truck for a long time. If the price of diesel were to go up, it would take me a while to either find a new vehicle, or find a new way to work, or change where I work. All of those things take time. So in the short run, I have to get to work. I have to drive my truck. I've got to get diesel. In the short run, I might be able to do things like save my shopping for one day a week so that I'm not making multiple trips to the store. But that would make a small decrease in the quantity demanded of diesel relative to my overall consumption. And the last of the factors we'll talk about now is the share of the consumer's budget. If it's a small portion of the budget, then that good is more inelastic. We don't consume very much of it, so it's hard to give up even a little bit of it. If that item is a larger portion of our budget, then we're much more likely to have flexibility to be able to give up a part of that in our budget. So if it's a large portion of our budget, it's more elastic. All right, I promised you we'd do some calculations. So I've got our demand equation from chapter 2. And let's say we have 2 points. I'm going to call them point number 1 and point number 2. Point number 1 is going to be at a price of $5, and point number 2 is going to be at the price of $6. And we're wanting to get a measure of the price elasticity of demand. To do that, I need to have the quantity demanded at each of these prices. So I'm going to plug in those values and find out what the quantity demanded is. So I plug 5 in for the price of beer. 215 minus 25 is 190. And then I'm going to do the same thing with the 6. 215 minus 30 is going to give me 185. We're actually going to look at a couple of different ways to calculate elasticity, and there are pros and cons to each of these. It also depends on what information we have as to which one of these we will use. The most common way we're taught to calculate elasticity is the simple between 2 points method that we've talked about on the first slide. So the change in quantity over the original quantity, the change in price over the original price to give us an elasticity. So let's do that here. Point number 1 is going to be where we started. Point number 2 is going to be where we ended up. In other words, we're saying the price increased from $5 to $6. What happened? So my quantity 2 is 185, quantity 1 is 190. Where I end up minus where I start over where I start. This is how I say it to myself every time. Where I end up minus where I start over where I start. That's how you calculate a percent change. And then if you want to turn it into a percentage, you would multiply by 100, but we'd have 100 over 100, and those would divide out. So we just leave it like this. This gives me minus 5 over 190 and 1 over 5. This guy is my big divide there, so I can flip and multiply. That's going to give me minus 25 over 190, and that is minus 0.13. So this is inelastic. The consumers are not very responsive here. We have an increase in price of 20%, and the quantity demanded only goes down by a few percentage points. If I'm looking back to that total revenue rule, we know that we could increase the price then from $5 to $6, and that would increase the total revenue. Now, there's an issue with this form of calculation. If I go from $5 to $6 and get this calculation, I get minus 0.13. If I go from 6 to 5, meaning I made this my number 1 point and this my number 2 point, because those denominators are dependent on where you start, I actually get a different value, which is not really great if you're a firm who's trying to use elasticity to make decisions. So there is another form of calculation that uses 2 points like this, which I'll touch on just briefly. This method is called the arc elasticity. The key difference between 2 points method and the arc elasticity is that denominator. What you should notice in that denominator is that they're taking the 2 points and they're dividing it by 2. In other words, they're using the midpoint in each of those denominators. So the calculation would look very much the same, but we're going to get a slightly different result. And this actually allows us to get the same number going forward or going backward. So I'd still do 185 minus 190, but in the denominator, I'm going to say 185 plus 190 divide by 2. And then I'll do the same thing for the price. 6 minus 5 over 6 plus 5 divide by 2. And if I simplify this, I'm going to get minus 5 over 187.5 and 1 over 5.5. I can flip and multiply. If I flip and multiply, I get minus 27.5 over 187.5, which happens to be minus 0.14. Now, in this case, it was a very small difference, but we were also going only $1 difference. So it really wasn't a huge move along that demand curve, but it allows us to have the same value going forward as it is going backward. And again, that's still inelastic, so we haven't jumped across the unit elastic point with this. There's another way that we can calculate elasticity that is often useful, and this is calculating elasticity at a particular point. I'm going to derive that for you here, but suppose you only have the demand curve and you have a single point. Instead of having to get another point, would you be going forward? Would you be going backward, right? For example, suppose you had the price of $6 and you had our demand equation from above. You have a price and a slope, but would you go the price down to $5, the price up to $6? Would you use $5.50? Would you use $6.50? If we rearrange this equation, we can get it to where we can use this as a point slope form instead of having to use 2 points. So I'm going to do just a little bit of derivation just because I want you to see that this is coming from the same equation that we already had. I'm going to take Q2 minus Q1 over Q1 and leave it right there, and I'm going to flip the denominator and multiply. So P1 over P2 minus P1, I can do that, right? That's just flipping and multiplying. And then I'm going to rearrange things. So I'm going to do a little example here so that you'll buy what I'm going to do up here next. Suppose we have 1 divided by 4 times 2 over 3. We would get 2/12. If I had 1 over 3 times 2 over 4, I would still get 2/12, right? Because this is multiplying straight across, I can change which fraction has which numerator. So I'm going to do P1 over Q1 times Q2 minus Q1 over P2 minus P1. So P1 over Q1 would be what's the price and quantity at that point of interest. Q2 minus Q1 over P2 minus P1 should look familiar. That's actually the slope. So I'm going to write it this way. Elasticity can be slope times P over Q. And we need to be sure we're careful about this. This is the slope when we've got quantity on the left and price on the right. I know that because quantity is on the top and price is on the bottom. Remember, slope tells us when the price of beer goes up by 1, quantity goes down by 5. That's how we read that slope. So let's do the example here that I started. At a price of $6, we already know the quantity is going to be 185. We found that earlier. So the elasticity is going to be minus 5, that's our slope, times price, which is 6, and quantity, which is 185. So I get minus 30 over 185, or an elasticity of minus 0.16. So at $6, our demand curve is inelastic. We know then we could increase the price just off that 1-point slope formula. There's another thing we can do with that elasticity that can be very helpful. We can estimate, given a percentage change in price and an elasticity, we can estimate a percent change to the quantity demanded. I'm going to rearrange this formula just to make it easier to see. I'm going to solve for the percentage change in quantity. So the percentage change in quantity is the elasticity times the percentage change in price. I know it seems like a lot of formulas, but it's really just a couple of formulas that we rearrange. So let's say that the price of apples increases by 2%. And I know the elasticity for apples The own price elasticity of demand for apples is minus 0.3. Apples are fairly inelastic. We need that healthy food, right? An apple a day keeps the doctor away. I want to estimate what the impact is going to be on the quantity demanded. So my percentage change in quantity is going to equal negative 0.3 times my percent increase in the price of apples. This comes out to be minus 0.6. And how do we interpret this? We would say a 2% increase in the price of apples is estimated to decrease the quantity demanded of apples by 0.6%. I don't have to put a minus here because I've already said it's going to decrease that demand for apples. I've got two more types of elasticities I want to talk about, but recognize that this concept can be applied to many other things, and it doesn't even have to be things that are about demand. It could be how close do people want to live to the city given a change in access to public transportation, right? We can use these elasticities for lots and lots of other things. The cross-price elasticity of demand is how responsive is the change in quantity demanded for one good when the price of another good changes. So this concept of cross-price means between two goods. If that cross-price elasticity is negative, those two goods are complements. Remember, the consumption of those two goods move together. So if the price of the one good gets more expensive, they're going to consume less of that good. That means they're also going to consume less of this current good because those two things are consumed as complements. If it's positive, then those two goods are substitutes. So if the price of apples goes up, I consume more bananas. So let's do a calculation. Let us suppose there's an increase in the price of apples at 3%, and that causes the quantity demanded of bananas to increase by 2%. We know right away that this is going to be a substitute scenario, not just because we eat apples and bananas, but because when the price of the one good goes up, the quantity of the related good also goes up. So let's calculate the elasticity. It's the quantity of bananas, price of apples. Right? We're talking about what happens to bananas when apples change price. So we've got 2% over 3%, or 0.67. It's not elastic, but it's more responsive than some of the other things that we were looking at this point. This means that there are some folks that are just going to continue to eat apples and not shift over to bananas. Now, what does that look like on our graph? I just wanted to put this out here so that you could see how this relates to the material we were discussing in Chapter 2. If the price of apples goes up and bananas are a related good, we know that's going to cause our demand for apples to shift to the right. So we have our initial demand in red, our new demand in blue. This is the market for bananas, so the price and quantity are of bananas. What we're getting here is how responsive this demand curve is to a change in the price of apples. So how big is this shift going to be because the price of apples has gone up? So let's look at a second example. For this second example, I want to talk about using a percentage change in the price of apples and an elasticity to estimate the impact of the change on the quantity of oranges. So suppose that we have a percentage change in the price of apples that is 2%, and the elasticity for oranges as it relates to the price of apples is 0.2. Okay, that sort of sounds like substitutes. They are, but definitely not perfect substitutes, right? We've got a small change in oranges when the price of apples change. Apples don't have some of the things like vitamin C to the level that oranges do and things like that, so people aren't as willing to substitute towards oranges when the price of apples goes up. But they will shift some, and so we want to calculate that. We want to see what is the percentage change in the quantity of oranges given this change in the price of apples. So what I'm going to do is take our equation from up above and rearrange it like we did on the other page. I know that the percentage change of oranges is going to be approximately the elasticity of oranges as it relates to the price of apples. times the percentage change in that price of apples. All I've done is rearrange that equation up above again, just like we did before. And you really can just remember this as the percentage change in quantity is the elasticity times, it doesn't even have to be price. We could be measuring something else on the bottom there, like income, but whatever that variable is on the bottom is going to be the thing that goes over here after the multiplication sign. Okay, so our elasticity is 0.2. Our price increase was 2%. Oranges will increase in consumption by 0.4% when the price of apples increases by 2%. I do want to take a little detour to talk about estimating revenue changes, and I'm going to do a little bit of wonky derivation here. But I want to get to where they got with this one equation in the book, and I want you to at least have a sort of a general sense of where it came from. I'm not going to do all the calculus behind how you really get there. I want to walk through this in more of a intuitive sort of fashion. So estimating revenue changes, I have revenue is price times quantity in my head, right? We know this, we think about this all the time. If we're looking at one good, let's pretend that good is X. I'm going to put a bunch of X's in here. It's the price of good X times the quantity of good X. We're going to start with one good, and then we're going to move into two goods. The formula in the book is related to two goods, and what happens if the price of a related good goes up to the revenue. So I want to be sure that we kind of get a sense of where they're coming from to get this. Now, without doing the calculus, I just want to walk through this. If you've had the calculus, there's some partial derivatives going on here. If I want to think how much does revenue change when the price of a good changes, I want to think about each of these two pieces independently. So for this first piece, I could say how much does revenue change straight from the price change. I'd want to know then the percentage change in price and the impact that that has on revenue. In other words, how much does price go up? Does it go up 1%? If it goes up 1%, then 1% times my revenue is how much more revenue I have. But then remember that increase in price would have an effect on the quantity. So this is estimating the impact of just a straight increase of price, assuming no impact on quantity, but we know there's going to be an impact on quantity. So the second piece of this is to say, how much would the quantity change given that change of price? And that percentage is going to impact my revenue. So if price goes up by 1%, I get 1% more revenue, but if that causes a decrease in the quantity by 0.2%, then I have a minus 0.2% times that revenue, and the balance of that, the sum of that, is where I end up with a total change in my revenue. Now, I want to be able to talk about this without having to do this in terms of quantity. So I'm going to go back to that equation we were just looking at a second ago where we had the percentage change in the quantity equals elasticity times price. And I'm going to substitute that in here. So this equation becomes the percentage change in the price of X times the revenue plus the elasticity times the percentage change in the price of X. I keep dropping that percentage change. I apologize for that. Times the revenue. This is going to give us how much price changes revenue, and this is going to give us how much the quantity changes revenue. So just for the sake of demonstration, let's work through an example. Suppose that our one good is apples and that our revenue for apples is $5,000. We have an increase in the price of apples of 1% and the elasticity of apples with respect to apples, or our own price elasticity, is minus 0.5. So just knowing that the price of apples is going to go up, we know there's going to be an impact on revenue. It might be positive, it might be negative. We'll see what happens, right? Because we're in that inelastic range, we should be able to know that that change in revenue is going to be positive. But let's calculate it. So our change in revenue is approximately 1% times 5,000 plus that negative 0.5 times 1% times 5,000. So the price effect is $50. I'm increasing my price by 1%. I get $50 more. Makes total sense. My quantity effect is half of 1% of $5,000 or minus 25 because I'm consuming a little bit less quantity, right? I'm consuming a 0.5% less quantity. Minus 0.5 times 1%, it's a 0.5% less in quantity demanded. So my net change is a positive $25 to revenue. And I knew that going in it should be positive because I had an inelastic demand curve and I'm increasing the price of the good. I want to finish out the derivation. I'm jumping back up to this line here because I want to be able to show you how they got to the formula that's in the book. So I'm going to take this formula and all I'm going to do, I'm just going to use the associative property here to do a little bit of grouping. I've got my change in revenue of X. Notice I have a percent change of P and a percent change of P. So I can factor that out. The percent change in the price of X is the revenue plus the elasticity times the revenue. I could actually go one step further, and I'm going to just to be able to get this in the form that's going to connect us to what was in the book. So percentage change in the price of X. I'm going to factor out Rx, but I'm going to leave it inside here just so you see the formula as it relates to the book here coming up. This is the estimated change in revenue when we change the price of a good. This is if we had only one good. Now, they don't actually show you this formula in the book. They do show you this with two goods, but I wanted to start with one good just so you could kind of see where this came from. If I'm talking about two goods, then my revenue is now the revenue for X plus the revenue for Y. The revenue for X plus the revenue for Y is really the price of X times the quantity of X plus the price of Y times the quantity of Y. And we want to see what happens to revenue. How does revenue change when the price of X changes? So how much does revenue change when the price of X changes? We already know what that looks like for our revenue for X. So actually, I'm going to just copy that down from above, and I'm going to use blue to help us see the different pieces here more easily. So I've got the percentage change in the price of X times the revenue times 1 plus that elasticity of X with regard to its own price. That's that first piece. The other piece of this is the part that has to do with Y. So how does the revenue for Y change when the price of X changes? Well, the price of X is going to impact the quantity of Y. It won't directly impact the price of Y, but it'll directly impact the quantity of Y because consumers will substitute away from or towards a good depending on the price of related goods. So we want to know what the percentage change in the quantity of Y is because that price changed of X. The price of X changed. And we're going to multiply that by the revenue of Y. I'm sort of ignoring these now that we've gotten down to where we're using the revenue. I just wanted you to see it kind of broken down like that. So you could see this is really what we're talking about being affected, that quantity, but quantity is part of revenue. And I'm again going to use that formula where we can say the percentage change in quantity is the elasticity times the price. In this case, it's the quantity of Y. The elasticity of interest is the elasticity of Y with respect to the price of X, and our price is the price of X. So I'm going to rewrite this piece. Now I'm just going to substitute in the percentage change in the quantity of Y. That's the elasticity, and I'm just going to put Y in X, knowing that's the quantity of one and the price of the second, times the percentage change in price of X times the revenue of y. There is a common piece here, right? We see the percentage change in the price of x over here, the percentage change in the price of x over here. So I can factor that out, and my change in revenue becomes the percentage change in the price of x, big parentheses, the revenue of x times 1 plus the elasticity of x with regard to its own price, plus, what do I have left over here? I have the elasticity of the quantity of x with respect to the price of, the elasticity of the quantity of y with respect to the price of x times the revenue of y. That's how they got to that formula in the book. There's really some calculus behind it, but I just wanted you to have a general sense of where that came from. Now that we've come up with this equation, let's work through an example associated with it. So suppose we have apples and oranges again. The revenue for apples is $5,000. The revenue for oranges is $1,000. The price of apples is increasing by 1%. And then we have to have our two elasticities. So the elasticity of the quantity of apples with respect to the price of apples, or the own price elasticity, is minus 0.5, and the elasticity of oranges with respect to the price of apples is minus 0.25. So what would we expect to happen to revenue for this firm if these are the conditions that they're facing? The change in revenue is 1%, or 0.01, times 5,000 times 1 plus a minus 0.5, that's the own price elasticity, plus the cross price elasticity, minus 0.25, times 1,000. This works out to be 0.01 times 2,500 minus 250, which is 0.01 times 2,250, or the change in revenue is expected to be about $22.50 if they are to increase their price by 1%. So the revenue will go up, and it'll go up by $22.50 approximately. The third and final elasticity we'll talk about in this video is the income elasticity of demand. How much does demand respond when there's a change in income? And we know that if that change is positive, then that is a normal good. When income goes up, the quantity demanded of that good goes up. And if we get a negative elasticity, that good is an inferior good. When income goes up, people want to consume less of the good. So this should look very familiar to you. We're not going to spend too much time on it, but let's do just a couple of calculations. Suppose that income goes up by 3%, and that causes an increase in the quantity demanded of some good by 4%. Our elasticity is that 4% over 3%, or 1.33. We know a couple of things by looking at this. The sign is positive, so this is a normal good, and this in absolute value is greater than 1, so this is an elastic response. That income elasticity of demand is measuring that shift in demand for us. How far did that demand move because of income? We'll do one more example. In this example, we're going to try to find the responsiveness of quantity when we know how much income changes and we know an elasticity. So suppose we have an increase in income of 3% and elasticity is 0.7. What would be the percentage change in the quantity demanded? Well, like all the other formulas we've looked at, it's percentage change in quantity equals elasticity times whatever that thing was that was in the denominator. So our elasticity is 0.7. The percentage change in income is 3%. We get 2.1%. That means a 3% increase in income is going to cause consumers demand approximately 2.1% more of the good, or a rightward shift of that demand curve. There are tons of other elasticities we could calculate, as I've mentioned before, so we'll leave that there. It gives you enough tools that you can work through some problems on your own. There's one last thing that I want to demonstrate for you, and that's how to calculate a regression equation in Excel, and then use that regression equation for your elasticities. The first thing you need to have is the data analysis tool pack enabled in your Excel. So these are the instructions for how to do that. You go to the File tab, Options, Add-ins, go, check the first two boxes, and hit OK. I'll walk through that over in Excel, but I wanted to put this in this video so you had it if you need it. All right, this is a file that came with our textbook, and we have some data here on milk sales. With milk sales sagging of late, the Milk Processor Education Program decided to move from the famous Got Milk slogan in favor of a new one, Milk Life. The new tagline emphasizes milk's nutritional benefits, including its protein contents. The MPEP began collecting data on the number of gallons of milk households consume weekly in millions, the weekly price per gallon, and the weekly expenditure on advertising in hundreds of dollars for the period following the launch of the new campaign. So our Q column here is the quantity of milk in millions of gallons. The P is the price per gallon, and A is their weekly advertising on milk in hundreds of dollars. So move the decimal point 2 places to get to actual dollars. If you don't have that data analysis tool pack in, this is how you enable it. File, Options, Add-ins, hit the bottom button here. It says Go, check the first two boxes, and hit OK. We're going to run a regression model that shows the impact that price and advertising have on the quantity consumed of milk. So I'm going to go to Data, Data Analysis, scroll down until I find Regression, and hit OK. When the dialog box pops up, we want to read this carefully. It says the input Y range. That's the variable we're attempting to predict. So in this case, it's our quantity. Always include the labels of your columns because that will give you labels in the output. So I'm going to highlight that column, and then I want to highlight the other two columns as the X variables. These are factors that we believe impact the quantity demanded. So I'm highlighting P and A, Control-Shift down arrow highlights for me just the data. And then I'm going to check this box that says labels because I have labels, Q, P, and A that I highlighted in row 2 there. That's all we have to do. We hit OK. We're going to get regression output. So here's our regression output. I'm going to zoom in just a little bit in case you need to see that closer. This piece here is what gives us our regression equation. But I want to do something else here before we get too excited. I want to look at the p-values associated with the coefficients. Now, the two coefficients of interest really are A and P. So I'm going to look at their p-values. Their p-values are really small. If you've had a statistics course, you know what that means. That means these coefficients are statistically significantly far away from 0. That means I can rely on the interpretation of this fairly well. When the price goes up by $1, I can believe the quantity demanded is going to go down by about 1.6, in this case, millions of gallons per week. All right, we've got our regression output here. I want to write that in y equals mx plus b form. So I'm going to copy this and just drop it over on Excel for us. All right, now that we've dropped this over here, let's write out the regression equation. The y variable was quantity demanded. This 6.5 is the y-intercept, or the q-intercept really. I'm going to put in 6.52. And then I've got minus 1.61 times the price plus 0.005, I'm rounding to 3 decimal places there, times advertising. This tells us for each additional one, in this case $100, but each unit 1 goes up, this is what happens to the quantity demanded. So for each additional $100 they're spending, or 1 unit A, we're going to see 0.005 million more gallons being purchased. For each dollar increase in the price per gallon, we're expecting to see about 1.6 million gallons fewer consumed. I can use these slopes for elasticities. So for example, if I had the price of $3.40 per gallon and the advertising budget was $150, well, this is 150 in hundreds, so $15,000. What would the elasticity be? First of all, we have to calculate how much would be consumed because we need slope times P over Q to be able to get our elasticity. So I'm going to take that $3.40. I'm going to plug it in and I'm going to see how many units consumers are willing and able to buy when the price is $3.40 and there's $15,000 worth of advertising. If I do the multiplication and addition on this, I'm going to find the quantity demanded is 1.796 in millions of gallons per week. Now I can calculate the elasticity. The slope I'm interested in here, if I'm trying to calculate the own price elasticity of demand, is my slope that's in front of the P. So my slope is minus 1.61 times my price, which is $3.40, over the quantity, which is 1.796. If we simplify this, we get minus 3.05. This actually means that people are quite elastic with regard to milk at this particular price. What would you advise the producers to do? This method works really well for linear demand curves. If you have a nonlinear demand curve, a demand curve that looks more hyperbolic, then you want to use the log linear regression equation. Really what that involves is taking the natural log of each variable x and y, or p's and q's, and then running the regression model just as we did a moment ago. So to look at an example of this, I have some data on the number of tickets sold and the ticket price. Ignore the date, that's really just week 1, week 2, week 3 sort of thing and doesn't have significance. If I look at this data, I can see that this is not a linear demand equation. This looks a bit more of that hyperbolic shape I was talking about a moment ago. You can always drop in a line to get a sense of what this looks like. That's what a linear demand curve would look like running through that. This really looks a little bit more like it's hyperbolic or logarithmic. Look, the logarithmic model fits fairly well. So this looks like a case where I wouldn't want to say that the demand is linear. A linear would be maybe an okay approximation, but if I know it's log linear, then I want to be able to use that. To calculate the regression here, I want to calculate the natural log of the quantity. So in this case, the natural log of the number of tickets, and I want to calculate the natural log of the ticket price. And then I'm going to run regression of those two variables. In Excel, it's easy enough to do. If I do ln, I get the natural log function, highlight that variable, and I'm going to do just a simple drag and drop over. Because I put the columns right next to each other, I can do that. You can see that's pulling in the natural log of C2, and then I can highlight those two cells, double click on that at the bottom, and drag and drop that formula down. Now I can calculate a regression equation from the natural log variables instead of the non-natural logged variables. So I'm going to go to data, data analysis, regression. I want to pull in my number of tickets as my dependent variable and my ticket price as my independent variable. And that's all I need to do. Hit OK, and I'm going to get my regression output. Now the regression output here is going to look a little bit different. We've got natural log in here. Well, that's because we changed the name of the price. We want to put those labels in there. And the other piece that we want to think about here, this coefficient on our natural log of price. This is no longer just the slope. Because I've taken the log of the y variable and the log of the x variable, and this happens to be a logarithmic looking demand curve, this happens to be our elasticity for this curve. So I know the approximate elasticity along that entire demand curve is about minus 1.6. Go back to the data and look at that. That's not going to have that same inelastic, elastic, unit-elastic relationship that we saw with the linear demand curve because of that curve associated with the relationship between price and quantity. That's all for now. Thanks for watching.